Have you ever wondered what dictates the absolute physical limits of living creatures? Welcome to this explainer, where we're going to dive right into the biomechanics of scaling. We're going to figure out exactly how animals manage to grow to massive sizes, and in the process, we'll unpack the incredible biological engineering hidden right inside us that makes our human scale possible.
Let's start things off with a classic sci-fi movie trope. It's a fun, fundamental question to ask. Why don't we see ants the size of horses walking around? I mean, it's a terrifying but kind of awesome image, right? Giant insects just roaming the plains. But as you'll see, physics and biology strictly forbid this from ever happening. And the core reason comes down entirely to how their bodies are held together against the relentless, everyday force of gravity. To really solve this mystery, we first need to look at nature's 3 biological blueprints for how organisms support their bodies against gravity and mechanical loads.
So these evolutionary blueprints generally fall into one of 3 categories: hydrostatic skeletons, exoskeletons, and endoskeletons. Basically, nature gives you a choice between fluid-filled cavities, like you see in worms and jellies, or hardened outer armor for insects and crustaceans, or, finally, internal mineralized frames for vertebrates like us. Let's explore each of these kind of step by step to see why only one of them takes the prize for allowing maximum body size.
Okay, let's dive into this first one, hydrostatic skeletons. These systems use pressurized fluid, which is almost always water, inside a main body cavity to maintain their shape and produce movement. The organism essentially uses alternating circular and longitudinal muscle contractions to manipulate that internal fluid pressure. Think of earthworms, right? They are basically just highly coordinated, flexible cylinders of fluid.
Next up, we have the exoskeleton, which acts as a literal suit of outer armor. This is what you see in insects and crustaceans. It's a hardened outer integument, usually reinforced with stiff materials like chitin or calcium carbonate, and it completely encloses all the soft, squishy tissues. It dictates the body's entire shape from the outside in.
And finally, there's the endoskeleton. This is an internal scaffolding. It's honestly a lot like hidden steel rebar in a skyscraper, but it's completely covered by soft tissues. Found in vertebrates like you and me, it's an internal structural frame, usually composed of mineralized tissue like bone and cartilage. And frankly, it is a true marvel of biological engineering.
But let's rewind for a second. There are some serious limits to that first hydrostatic model. Let's look at the fluid weight trap and why hydrostatic skeletons fail miserably at supporting large bodies on land.
See, while a hydrostatic skeleton is incredibly flexible and works beautifully for swimming or burrowing underwater, it's a totally different story on dry land. A massive fluid-filled organism up here would simply collapse under its own weight, without the buoyancy of a water environment to help hold it up. Because they lack a rigid structural frame, they just don't have the tensile strength to hold up a massive volume against gravity. I mean, if a worm somehow magically expanded to the size of a cow, it wouldn't roam the earth, it would essentially just flatten into a giant, helpless puddle.
So, okay, if squishy fluid doesn't work for a giant creature, what about the rigid armor of an exoskeleton? What about our giant horse-sized ant? This seems robust, right? Armor is strong. Well, let's explore exactly why armor fails at scale.
The absolute crucial point here is that scaling up an insect means its chitin and calcium carbonate armor must become exponentially thicker to support the new load. As biologists are quick to point out, a body with such a huge volume would require an exoskeleton that was exponentially thicker and therefore infinitely heavier and clumsier. As an insect gets bigger, the sheer weight of its armor rapidly outpaces its own muscle strength. It severely restricts the internal volume, leaving practically no room for internal organs, let alone enough space to actually breathe.
And all of that brings us to the truly fatal flaw of exoskeletons, ictesis, also known as molting. Because the outer shell is entirely rigid, it literally cannot grow with the animal. To get bigger, an animal has to completely outgrow its rigid shell, produce a soft new skeleton underneath, and then shed the old skeleton in an incredibly dangerous process. During this time, they are completely unprotected and exceptionally vulnerable to trauma. Now picture this. If you're a giant, soft, molting horse ant, your own massive body weight might literally crush you against the ground before your new shell even has a chance to set.
Which brings us nicely to the winning evolutionary technology, the one blueprint that actually solves this massive scaling problem, the endoskeleton. The absolute key to biological scaling comes down to this concept of flesh in bone versus flesh over bone. With an exoskeleton, you have a flesh-in-bone dynamic. Overall body volume is heavily restricted by the internal cavity of that rigid outer skeleton. You are entirely trapped inside your own bones. But with an endoskeleton, we see a flesh-over-bone dynamic. Because the soft tissues sit on the outside of the endoskeleton, overall body volume isn't restricted by the skeleton itself. The bones are tucked safely inside, doing all the heavy structural lifting, allowing the flesh, fat, and muscles to grow massively around them.
Endoskeletons offer just unbelievable biomechanical advantages that make larger bodies entirely possible. By utilizing a concentrated structural layout, the body can handle heavy mechanical loads highly efficiently. And because muscles attach on the outside of the skeleton, it allows for significantly thicker, much more diverse muscular architectures. These external attachments create a greater distance from the joints, which provides massive, dynamic leverage for movement, plus the internal skeleton is safely cushioned from everyday trauma by all those overlying soft tissues. And crucially, there is absolutely no dangerous continuous molting required for juvenile growth. Your bones just grow seamlessly right along with you.
This internal layout also builds into a remarkably efficient support system. Because it's a compact internal network, your circulatory system can easily cover the entire tissue volume. The skeleton is continuously perfused. It oxygenates and feeds the bone from both the inside out via nutrient arteries located right in the marrow and the outside in via periosteal arterioles. This means your body can constantly feed and repair its bone structure without having to spread vast, unrealistic resources over a massive external shell.
And this brilliant biological engineering allows an adult human to walk around with 206 distinct bones. This highly specialized, surprisingly lightweight internal framework easily supports our body weight and facilitates continuous growth, all while providing perfect specialized attachment points for our wildly intricate muscular system.
Let's actually zoom in on the core of this system for a second. Just 80 of those 206 bones make up your axial skeleton, forming the incredibly sturdy central core of your body. This includes your skull, which is actually an intricate puzzle of 8 cranial bones protecting your brain, and 14 distinct facial bones. Right below that, your vertebral column features 24 individual vertebrae, ending with the sacrum and coccyx, wrapping around and protecting your delicate spinal cord. Add in the thoracic cage, with your sternum and 24 ribs guarding your heart and lungs, and you have an incredibly robust anchor. It provides the absolute foundation for gross muscular stability, like when you're sprinting, all the way down to the fine muscular stability required for something as intricate as human speech.
So we have this incredible internal structure that essentially solves the physics problem of getting big. But here is the ultimate nature of this living framework.
What you should really take away from this explainer is that an endoskeleton is absolutely not just a bunch of dead, dry rocks holding you up. Your skeleton is a highly dynamic organ system. Unlike the dead armor of an insect, your bones are actively living tissue. They are continually rebuilding themselves from scratch with blood ingredients and constantly breaking down to adapt to what you're doing. It is a literal biological miracle that you can move, run, and grow without being crushed by gravity. When you exercise, you are literally signaling your bones to reinforce themselves to handle heavier mechanical loads. They are constantly reacting to the demands of your environment.
It's this living, continuously adapting internal structure that makes our large scale and our incredible mobility possible. So, I'll leave you with this final, provocative thought. Knowing that your internal scaffolding is constantly breaking down and rebuilding itself to adapt to your specific lifestyle, what is your skeleton building right now?